Good evening, ladies and gentlemen. Welcome to the fibUK evening lecture presenting two major infrastructure case studies. Today we'll be presenting HS2's Colne Valley Viaduct and the Taf Fechan Viaduct on the A465 Heads of the Valley project, sections 5 and 6. I hope you can all hear me. Just going on to the next slide. Not sure why it's not going. Just bear with me. Okay, so we'll start with a couple of pointers on how to use the chat. You should all be seeing the live chat dialog box on your screens. I hope that's the case. You can post comments that will be seen by all in the bottom section. And more importantly, if you have questions for the presenters, you can use the question mark in the top right of the dialog box. Click on there, another dialog box will open and you can post your question. Don't forget to press send. And I'll be looking at the questions in the background and summarizing them for the presenters at the end. So, a quick intro to this evening's speakers, so we can get into the presentations as soon as possible. Presenting on HS2 Colne Valley Viaduct will be George Kapos, who is Market Sector Director for Rail for Rendell Limited. George is a civil and structural engineer with 19 years experience in both major infrastructure projects and in the process industry. He's worked in the UK, Europe, Middle East, and Australia. And he'll be speaking to you in his capacity as the engineering package manager for the Colne Valley Viaduct. So moving on to the Taf Fechan Viaduct, we have two presenters, Henry Still and David Arribas. Henry's an assistant engineer with Atkins. He's been involved since the beginning of his career in this project, in the Taf Fechan Viaduct. So he was involved in the tender design and the detailed design, as well as providing on-site design support. And representing the contractor for the job, we have David Arribas, the contractor for the job, FCC Construction, I should say. David has been with FCC for 25 years and has worked on multiple bridge projects around the world. And he currently leads FCC's Bridges Department. So, without further ado, I think we'll start with this evening's presentations, and I will hand over to George.
Hello, good evening, everyone. My name is George Kapos, and I'm the Market Sector Director for Rail at Rendell Limited. I've been working on the Colne Valley Viaduct as an engineering manager for the last six and a half years, and today I will be presenting some elements of the design as well as the current status in terms of the construction on site. Having a look at the agenda, I'm going to go through the project overview. I'm going to describe what HS2 is. We're going to go through the project requirements. I will briefly describe the scheme, and then we're going to go dive into the details of the design. And finally, I will share some photos of the construction. Starting with the project overview, I'm sure that most of you are aware of the HS2 project, but for those who don't know anything about the project, HS2 is Britain's new high-speed rail line that will connect London to a few of the biggest cities in the West Midlands, such as Birmingham, Manchester. It will extend all the way up to the biggest cities in Scotland, and it's currently the largest infrastructure project in Europe. It has been split into various phases. I'm not going to cover those phases now, but I will focus predominantly on phase 1, which is the one that I'm going to be talking about in terms of the viaduct. Phase 1 was split into 7 contracts. Our joint venture, Align, won contract C1, where I'm pointing with my mouse. So I need to open also the laser pointer. Contract C1 in that location here. Align JV comprises of three major contractors: Bouygues, Volker, Fitzpatrick, and Sir Robert McAlpine. And obviously, every contractor needs a designer, so they formed the line D with Align, Jacobs, Angerop, and Rendell. A few words about the contract, contract C1. It's a total length of 22 kilometers. We've got a 16 kilometers twin bore tunnel with 5 shafts and 43 cross passages. I'm pointing on the shafts with my mouse at the moment. 1, 2, 3, 4, 5. We've got a north portal at the north and the south portal as an entry and exit point for the train. We've got the Western Valley slopes, which is a big embankment and a cutting. And finally, the 3.4 kilometers of the Colne Valley Viaduct that we're going to cover today. A few words about the site overview in terms of the viaduct. The alignment, the line, the black line that you see in the plan view is the alignment of the viaduct. What I wanted to show in this slide is all the physical constraints. The viaduct will go over 4 lakes. We've got 4 rivers, the River Colne here and the New Year's Green Born in that location there. We've got the Grand Union Canal. We've got 3 roads, the A412 North Orbital Road in that location. We've got Moorhole Road here and Dews Lane. We're going over various utilities that we had to divert. We've got the Denham Aerodrome in that location here, and obviously a flight path in that location. We've got areas of special scientific interest, the AAA areas, as we call them, with ancient woodland, which we're not allowed to touch, as well as items that you cannot see in the plan view, such as dissolution features. A few words about the project requirements. Obviously, we had to design a structure which was buildable, a structure that was safe, a structure that can be easily maintained and durable. We had to take into account the minimum impact on the Colne Valley Viaduct area. Cost was another factor. Aesthetics was another one, as well as consents and in terms of our key stakeholders. On the right-hand side, you can see the winning tender design, which was reinforced concrete box girder, pre-stressed box girder with 40-meter spans. 1 month after the contract award, we received from HS2 a particular report, which was called the HS2 Specimen Design Report. In that report, there was a study with various options of the viaduct, as well as it was showing the preferred option, which was the specimen design that you can see here in this visual. Finally, we had 2 particular project specific requirements. One was we had to design a beacon structure for HS2, and the second one was that the structure, we had to design a structure of international significance. Obviously, this was purely an architectural report, so we had to make sure that we will consider these designs, and we had to engineer them properly. Going into the scheme description, I will start with the viaduct characteristics. We've got a 3.4 kilometers long railway viaduct. It's going to be the longest viaduct in the UK when completed. The height of the track level varies from 10 meters at the south all the way up to 17 meters at the north. We've got 58 piers and spans between 40 and 80 meters. The deck is a precast segmental post-tension concrete box girder that has been constructed by the balance cantilever technique. In terms of the foundations, we've got bore cast in place piles. 2 of the elements that we adopted from the HS2 specimen design were the main key character areas. On the Colne Valley, we have 2 character areas. One is the woodland areas, and the other one is the lakes. For that reason, we had to adjust our design in accordance with the landscape. What the woodland areas, we had to go for vertical piers and a maximum of on average an average spans of 60 meters. While where we have water, in terms of the lakes, we decided to go with this arch from deck structure and have spans that vary between from 67 to 80 meters. A few words about the deck articulation. The Colne Valley Viaduct has been split into 4 modules. Each module is approximately 900 to 950 meters long. Modules 4, 3, and 2 are about that length, with the exception of module 1, which is 465 meters. The decision for the 900 meters figure was based on the deck expansion and contraction due to thermal effects and time-dependent effects like creep and shrinkage, as well as on the maximum stroke of a conventional track work expansion device, a rail expansion device. What we were trying to achieve with splitting up the deck was we were trying to limit the rail structure interaction movements as much as possible, and reduce the number of rail expansion joints and rail expansion gaps, with the intention of enhancing safety and continuity on the rail. Each module has a fixed point at the center of the module. As you can see, as I'm pointing with my mouse here, so module 4 has a fixed point there, which is called fixed buttress. The same applies for module 3 and module 2. There's an exception on module 1, where we have a fixed pier, and this is located not in the center of the module, but very close to the abutment. You can see in the very simple schematic here how the fixed buttress is working compared to the other piers. What connects two consecutive modules together is an expansion buttress. This is a segregated structure. It's a portal frame structure, and I'm going to cover this in a bit more detail in the next few slides. We talked about module 1. The main difference of module 1 compared to the others is obviously the fact that it's half the length of modules 4, 3, and 2. It's approximately 465 meters. What we did here, we wanted to move the fixed pier close to the abutment in order to minimize the expansion length between the fixed pier and the south abutment. Obviously, this allowed us to remove the rail expansion joint, but when you have a continuous rail and a discontinuity of the structure, you have to confirm that you don't have any excessive stresses in terms of rail structure. There's no interaction, and hence we had to undertake a rail structure interaction analysis to confirm the stresses at the deck and at the truck slab system. Going into the Colne Valley Viaduct design, I'm going to start bottom up. We're starting with the piles. We have, with the foundations, we have 292 cast-in-place reinforced concrete piles. In some locations, in some pile caps, we have 4 piles. In other pile caps, we have 6 piles. They vary in diameter. Sometimes they are 1.8. They vary from 1.5 to 1.8 meters, and they are supporting a conventional reinforced concrete pile caps. They go up to 53 meters in length, and they're typically founded in chalk. We insisted a lot at the beginning to go for supplementary GI as well as low test piles, and that for those 2 reasons we managed to reduce the pile length from 60 meters that we had initially at scheme design to just over 40 on average, and that led to a substantial carbon saving of the order of 30%. A summary in terms of the foundation design as per BSA 1997 part 1. One of the characteristics is that these are friction piles, and the shaft resistance is based on the effective overburden stress in accordance with the Syria 574. We have ignored end bearing capacity due to the uncertainty with the dissolution features and voids, and we have considered a minimum factor of safety of 1.5, which was used expecting settlements of less than 1% of the pile diameter. Moving on to the substructure. These are architecturally stylized reinforced concrete pier stems that can go all the way up to 9 meters in height. It's a fairly complex geometry, as you can see in the isometric view. For that reason, we had to split, because of the complex geometry. It was quite hard to detail the piers, and for that reason we had to split the reinforcement into main core reinforcement and surface reinforcement. So the main core reinforcement, as you can see, that is this one over here that forms a cross, is able to take axial load and biaxial bending effects as well as shear. while the surface mesh is there to control early thermal cracking. We had also additional considerations in terms of the textured finish, as you can see on the photo on the right-hand side. Moving on to the fixed buttresses. If you remember, this is the structure that is located at the center of each module. This is the point of the longitudinal fixity. You can see the visual how this structure looks like. And in terms of the fixed buttress piers, these are inclined, reinforced concrete legs, and they have very similar geometric rules to the vertical piers in terms of the geometry. One of the fixed buttress piers contains a steel shear key at the top, while the other contains a shock transmission unit. So I'm going to explain why we have installed a steel shear key and an STU in the next slide. So we started initially with a monolithic arrangement for the fixed buttress pier, for the fixed buttress, as shown here in this location. This design solution was quite sensitive to soil stiffness. It gave us excessive foundations and very high stresses due to creep and shrinkage and thermal on the deck. So it was quite dependent on the soil stiffness. We had to change to an articulated configuration with the use of spherical bearings and steel shear keys. That way, we managed to reduce the dependency on the soil stiffness and optimize the foundations, but we were still getting high stresses at the deck due to creep and thermal. And finally, with the introduction of an STU and a steel shear key on the other side, we managed to overcome that obstacle again and reduce the effects of creep and shrinkage and thermal on the deck. I'm going to talk a little bit about the STUs. This is a simplified sketch that shows the 4 modules. The line in green is the fixed buttress pier, and this is the STU that contains that is contained on top of the pier. So the STU is able to transmit short-term impact forces such as braking or traction from the train, while at the same time it's able to permit long-term movements between the structures such as temperature, creep, and shrinkage. So the principle is similar to the one that we have on our cars, the seat belt on our cars, where we're able to move slowly, but during a sudden braking of the car, it locks. Moving on into the expansion buttresses. Again, this is the point where we have a physical gap, as you can see in the visual here. There's a structural gap, and also this is the point where we have the rail expansion joints. This is the point again where the module either ends or it starts, and it's the point where the expansion buttress or shares one of its sides. Both of these elements, either the end of the module or the expansion side, have independent bearings. As you can see in the isometric here, they have independent pier stems, but they are sharing the same pile cap. Again, these are fairly slender piers because we were trying to accommodate all the deck displacements and the volumetric changes due to the time-dependent effects and the thermal movement. Moving on to the superstructure. This is a single-cell precast segmental concrete box girder. It is able to carry a dual track with trains running at 320 kilometers an hour. It varies in depth. It goes from 6.7 meters at the piers all the way up to 3 meters at midspan. We have a constant width of 14.7 meters at the top flange and 6.5 meters at the bottom slab. We've got vertical webs and inclined panels. Something that is worth mentioning is that the inclined panels are not match cast, so they're not really contributing into the longitudinal inertia of the deck. However, they do contribute in the transverse direction during a particular load case, and that is derailment. So during derailment, when the train will derail, it will hit the robust curb. Hence, then the whole system, robust curb, top slab, inclined panel will act as one, and this is when the inclined panel will contribute. I will show you a few joints from the functional cross-section. The main reason why I wanted to share that is to show you what's happening on top of the deck. This is the functional cross-section with cant, and this is the functional cross-section with cant, but at the OCS mast location. I think it's worth talking about two elements. Well, I will talk about all the elements, but there are a couple of innovative elements here. One is the parapets, which is the element that you can see here. I'm pointing with my mouse. This is a UHPFRC parapet, which stands for Ultra High Performance Fiber Reinforced Concrete Parapet. With this type of material, we're able to achieve thicknesses of 50 millimeters in that location here, and it's unreinforced. We've got fibers obviously inside, and it's got this strange shape for aesthetic reasons. We've got the noise barriers in that location, OCS masts. We've got the cable troughs and the drainage troughs in that location, robust curb, and another sort of an innovative element is the protection slab, which is an SFRC protection slab. It's a steel fiber reinforced concrete slab that is able to work without reinforcement, obviously, and any forces that are picked up by the track slab are transmitted through those shear links onto the protection slab, and then from there via a shear key that we have very close to the robust curb, we're able to transfer the interface shear onto the deck. Moving on to the arch from deck. These are located over the lakes, as we've discussed before. Spans vary between 67 and 80 meters. They were inspired by the stone skipping effect from the HS2 design report that we mentioned before. The whole idea was to increase the sense of openness over the water and the views. Those elements are composed of two reinforced concrete legs forming a V shape, and they're connecting to a node in the center at that location, and they're supported by bearings on top of the piers. The bearings are located above the 1 in 100 years flood event plus climate change. One of the things that is worth mentioning is that although it looks like an arch, there isn't any arching effect in that bridge. We were trying to avoid that. Obviously, we don't have massive foundations to take this lateral thrust from the arch, so we designed those elements to act as D-beams. So the D-beam behavior means the lower chord of those elements acts in compression, and thus, and for that reason, it doesn't generate any lateral thrust in the foundations. Obviously, those piers move because of the volumetric changes due to creep and shrinkage, and when they move, obviously they will predominantly create a particular eccentricity at the location of the bearings at the central node. What we did in order to avoid that, we inverted the bearings. We actually turned the bearings upside down, so that the sliding element is located at the top of the pier rather than under the deck. With that configuration, the vertical reaction will always be located at the point of intersection of the lower chords of the arch from deck, and this improves substantially the structural behavior of the deck. Obviously, that way we are transmitting the eccentricity onto the pier leaves, onto the pier stems, but we have designed this out. Moving on to the pre-stressing, nothing fancy here. This is conventional pre-stressing system. We have two types. We have internal tendons and external tendons. We're using the top internal tendons for the cantilevering, for the erection side of things, and we have continuity tendons when we're doing the stitch for the closure. The reason why I wanted to discuss this slide is not so much in terms of the pre-stressing system, but because of the fact that we've used internal tendons. So internal bonded tendons are back in the UK after a 30 years ban. And how we managed to do that, obviously with protection level 3 tendons, which means what? We are providing polymer ducts, which provide leak tight encapsulation of the tendons, and together with the cement grout, They are providing a particular level of protection, but on top of that, we are able to monitor the integrity of the encapsulation by doing impedance testing and monitoring the resistance at the tendons. Moving on to the next slide, these are external tendons. Again, conventional system here. They span over 2 spans. The largest cable goes up to 160 meters. Quite big strands, quite big cables over here. We have 37 strands. Again, the reason why I wanted to discuss these is mainly in terms of I wanted to highlight the replacement. It is worth noting that the replacement of the external tendons can be done with a monostrand jack on a strand by strand basis, which means that external tendons can be replaced during operation while the trains are running. A few words about the Colne Valley Viaduct construction. So as part of the HS2 design philosophy, it was recommended to use prefabricated construction where possible. This gave us various benefits in terms of the construction quality, since the segments were produced in a controlled environment. It reduced hazards, and it minimizes the financial and the environmental cost. The viaduct is constructed with the use of a launch and gantry. We used this 700 tons machine. It was kind of like recycled. It was used before in Hong Kong and Singapore. We had to dismantle it, ship it out to the UK and erect it again. All the segmentation and the deck segments are tailored we're tailored to the launching girder. The precasting yard, this is the yard which is responsible for the delivery of the 1,000 segments that we have. There are mainly 3 activities that are happening. One is the delivery of rebar in the precasting yard, and then we're doing the rebar cage assembly. You can see the jigs here and how they're assembling the cages. Second is the casting of the segments. You can see the cells. This is where they pour the concrete, and then finally they're doing the finishing and the storage. We did use a lot of 3D rebar modeling in the design. This was inspired by the nuclear sector. We produced more than 3,000 segment catalog drawings and more than 1,800 deck reinforcement drawings. All the 2D drawings were coming out of the 3D rebar modeling, and they were used on site. So a few words about the 3D modeling. Some of the benefits in terms of the design. We were able to assess the overall constructability, resolve clashes with inserts, tendons at various stages. It helped a lot in terms of the communication at an early stage with the contractor. We did produce 2D drawings out of those 3D rebar models. It enhanced health and safety, and also it was one of the tools that the category 3 checker used in order to check the design. Going into the construction, again, various benefits here. Again, the contractor used it from an early stage. It really enhanced the communication between the designer and the contractor, and we managed to share ideas both ways. It helped them a lot with the prefabrication. It helped them plan the works more efficiently, and nowadays everybody on site have got tablets. They're able to point with their tablets in a particular segment, and with a particular software, all the 3D rebar of that particular segment appears. I'll show you a few photos of Colne Valley Viaduct construction. I'm going to start with the piles. This is the pile bore machine. You see the cage installation in those 2 photos, and then with the concrete pouring. Again, moving on into the pile caps, we've got the sheet pile installation all around it, cropping of the piles, then installation of the blinding, and then rebar and concrete pour for the pile cap. Substructure piers. This is the fixed buttress pier. You can see the complexity in terms of the reinforcement in this rebar cage. We've got the shutters, the formwork on the middle, and also the final concrete finish on the right hand side. I have a few slides to go through a typical cantilever span erection I'll go through these quickly. I'm conscious of time. We're going to start with the installation of the temporary props on a particular pile cap, as shown here. After that, the front leg of the gantry is moved and it sits on top of those temporary props. Next stage is to erect the segment over piers, or SOPs as we call them. We install the PT nailing system and we connect the SOPs to the piers. We fix them to the piers. Next stage is to move the gantry support on top of the SOPs. And at that configuration, now the gantry is able to start the balance cantilevering. We start with the first segments, the so-called S1 segments, as you can see here or in the photo in that location, and we are installing the temporary nailing for the cantilever stability during erection, as you can see in that location here. After that, all the segment pairs will start getting erected. Obviously, we are applying epoxy to the match cast joints, and temporary prestressing is installed to support the segments. We repeat all the cycles for all segments, and we reach the cantilever on the adjacent from the adjacent span. Next step is to do the stitch formwork, as you can see here in the photo. We pour the stitch, and the next step is to install and stress the permanent internal continuity tendons at the bottom slab. Once all the internal continuity tendons are stressed, then the gantry is able to start launching again, and from that point onwards, we are able to start using the trailer, which is the machine that is able to transport the segments all the way up to a certain point where the gantry is able to lift it and put it in place. And after that, the whole process will be continued again. The gantry is moved on the next pile cap, and it's exactly the same cycle. Last slide is a few current photos. This shows the viaduct at the woodlands areas where we have vertical piers, haunch deck, 60-meter spans, and this is a thing where the gantry sits at the moment over one of the arch from decks. Thank you very much.
Oh, thank you for that. So my name's Henry. I work with Atkins Realis, and I am Taf Fechan's lead designer at the moment in time. And I'm going to talk you through the design side of Taf Fechan Viaduct, and then I'm going to hand over to David Arabus, who's the head of bridges at FCC, who's going to cover the construction side. So Taf Fechan Viaduct is part of the A465, if the slide wants to advance. Yeah, so the A465 is a key route connecting Swansea with Hereford. It was originally constructed as a 3-lane road consisting as a single carriageway with a climbing lane, and then all the junctions were at grade. So it formed a key part of the South Wales trunk road network, and because of its importance, they decided that it needs to become a dual carriageway with grade separated junctions. So the scheme was split into 6 sections, and the first widening started on section 4 back in 2002. Since then, the various sections have advanced and widening has been completed, leaving just sections 5 and 6. Now, 5 and 6 is a particularly challenging section. Whilst not particularly long, it does go through some of the most deprived areas in Wales. The road is immensely congested, especially now with the roadworks, if you ask any of the locals. And most importantly, the terrain is incredibly challenging. Whilst it's only 18 kilometres long, this section of dualling, we do have 36 bridges and 4 refurbished bridges with a whole variety of different structures going on. So we've got a multi-span weathering steel viaduct, we've got a 70-metre integral, we've got some normal pre-stressed beams and some typical footbridges, and then of course we've got a post-tensioned balanced cantilever viaduct. So who's involved in the scheme and why should you listen to me about it? So my name's Henry. As you might have noticed, I don't have a Welsh accent. Hate to disappoint you if any of you came for that. I originally grew up in Brighton and then moved to Swansea to study civil engineering. And as part of my course, I had a year in industry placement, which was with Atkins in Cardiff. Now, at the time, they were working on the A465 tender, so I got involved with a load of work on that, carrying out different value engineering tasks. And then I went back to Swansea and got my master's. I then returned to Atkins, where I then dived straight into the design as it was kicking off, and was part of a small team of very talented engineers working on Taf Fechan Viaduct. After 2 years, the design was finished, handed over to the contractor, and I then went up to Merthyr Tydfil, where the site office is, to aid them on site to help with the construction. So you'll be probably wondering all these different logos and who they are. So the Welsh Government is the primary client, and FVC, or Future Valleys Construction, is the principal contractor, of which FCC is part of that consortium. Atkins Realis was formerly known as Atkins. We rebranded on Tuesday, so if you're wondering who they are, that's who we are. And then Tekazam and BBR are the subcontractors on site responsible for building Taf Fechan Viaduct, and Senna was the cat-free checker. So a wide range of companies. I've probably missed a couple. I'm sorry if that involves you. So moving on to the viaduct itself. As you might notice, compared to the one we've just watched, it's much, much smaller. It's nowhere near as 3.4 kilometers, whatever it is. Instead, we have 3 spans, which was 56 meters, 75, and 56 again. It consists of the eastbound onslip, eastbound mainline, and westbound mainline. The eastbound onslip is coming to join the structure and merges with the other 2 decks halfway along, which creates some interesting geometry. If you're wondering where the westbound offslip is, that's currently the existing structure, and that's going to be repurposed into the offslip. Now, a key part and key difference between Taf Fechan Viaduct and the HS2 viaduct we just looked at is that this is a post-tension balanced cantilever cast in situ, so there's no precast segments on this. A key aspect of this design is that we'll build the piers and then get to segment 0, or the hammerhead as we're calling it, and we'll then cast a segment on the east side, cast a segment on the west side, tension the top tendons, and then repeat the same process again. So our segments in total are are 6.4 meters. The closing segments are slightly shorter, and we have 5 segments cast from each from each pier, excluding the segment 0. So how we've gone about modeling this is we've got a very complicated load model. So in this model, we don't just have the 3D geometry, we also have the time aspect. So we have 107 construction stages in this model. It starts off as a line beam, and as you go through the construction stages, it eventually becomes a full-on grillage. And then to add even more complexity to this model, we've even modeled the tendons within it. Now, this had some very key advantages. It allowed us to check the SLS conditions very quickly, so that we could quickly run through, adjust tendon profiles, see what the overall SLS stresses were, and then rework them if they weren't working. It also allows us, because we've got time, to calculate the tendon losses directly in the model to help with the ULS design. And of course, it's also helping with pre-camber. I can just run a button, it spits out all the pre-cambers. I can hand that over to David, and he can go and instruct the team on site to build them as such. So I'm going to dive into a little bit of the various elements of the structures and hopefully give you an insight into what governed their design. So as you can see, our piers are actually quite tall and quite chunky. It's now 35 meters. I can assure you might not sound very much, but when you're walking up those stairs, it sure is tiring. So what governs the design of this is the outer balance condition. Because we don't have a bearing at the top of this, the entire moment is held by the piers. So once we've cast one side and not the other, combined with the loading of the travellers and any wind loading and any other sort of outer balance condition, the moment at the bottom of the piers is very large. And as a result, we've had to increase the size of the box. So our box stands at 3 meters in width and 7 meters wide. Now, also, a thing that has also governed the design and why it looks like there's so much steel there is that during initial design stages, we were asked, can we make it so that we pour one of these 5-meter segments every 2 days? Now, the design office laughed at that, but I've since been proven wrong. They can easily do it in 2 days. And I'm sure if the team were really trying, they could probably do it in 1. But So as a result, we've got this special concrete mix with very high cement content to gain early age strength quickly so we can keep up this pace. And that has in turn influenced the early thermal design. If you're wondering what the windows are, that is actually for the formwork to cast the initial segment. They'll eventually be closed up and eventually piers sealed, and you won't ever need to go in them again. So focusing on the abutment design, we have 3 abutments because of the onslip. So the 2 on the west side are pad foundations on rocks with a retaining wall, approximately 10 meters in height. They do differ a little. And then on the east side, we have a piled abutment. They're founded on rock. Piles are, I think, 25 meters in length and 1.2 meters in diameter off the top of my head. And as you can see there in the top corner, we've got a 400 meter cube base being poured, which is for the west main line abutment. So moving on to the deck segments, effectively what we have is 3 separate bridges that end up being stitched together. So we have 72 segments, again, 6.4 meters long, where we got tensioning in the top slab, and top of the webs, and the bottom slab. So this box ends up being it's 4.5 meters deep at the piers, and it goes to 2.5 meters towards the center span. The webs are also changing in size. So over the pier, they stay at 700, and that's to allow tendons to anchor in there. Meanwhile, in the center of the span, we drop to 500 mil because we just don't need that sort of thickness. So moving on to the post tensioning, which is really where the bridge gets its strength from. We have tendons in the top slab and bottom slab. The top tendons are tensioned as we go along, so we'll cast the balanced segments, tension them up, move out, and then repeat the same again. Meanwhile, the bottom tendons, we can't do that because evidently we're not connected up. So these top tendons help in the hogging case, bottom tendons in the sagging case. And the way we've done this is we have 19 strands that are high strength steel, which get pulled by a hydraulic ram at the different anchor points. So because we have 3 decks, all with different curvatures and different widths, it ends up as 3 pretty much unique tensioning designs where we've tried to standardize where we can. So the bottom continuity tendons, for example, always end in these blister elements that we can see in the bottom of the slide here. Now, these tendons try and stay in a straight line. They follow the bottom slab, and then when it's time to reduce the amount of post-tensioning in the segment, we bring it up into the blister where it goes into a thing called a trumpet, and that's where it ends, and it gets cut off. So the post-tensioning in the top slab has to work a little differently. Because of the tendons and the high force concentrations from where these are being stressed, we need a lot of bursting reinforcement around the anchors. Now, because the slab's only 300 mil thick and 350 mil above the box, we can't end them in the slab wherever we like, and instead have to be ended over the webs and in the haunch. This results in this sort of curvature dance going on of the tendons moving sideways and trying to get to the webs. Now, this in turn would induce lateral shear forces if they weren't symmetrical. So we try to keep that as symmetrical as we can to aid through the design. The curvature requirements on site have some very high precision. We have to work to a 5mm tolerance of the ducts to ensure that we aren't inducing any forces that we didn't intend to. Also, due to the arrangement of the box, our wings are actually quite short, and so the amount of tendons we want to get in there, we can't actually fit where we need to. As a result, we even have some tendons in the webs over the pier, which, whilst compromises on effective depth, was the only way to get the required stressing with the limited width we're working with. So focusing a little more on the post-tensioning anchors now. You've got a high stress concentration in this location, and so we've got to have a way to deal with this. So we have the white duct, which you can sort of see in that picture there, go into the metal trumpet. Around the metal trumpet, we've got the helical bars and then some bursting links around that. And in the case of the top tendons, where they're finishing in pairs, we've got another set of bursting links around the pair. Now, unlike the high-speed 2 viaduct we just looked at, we don't have any external tendons. They're fully internal, and that has come with a load of requirements. So again, we've got the polymer ducts like HS2 did with its internal tendons. And then we also make sure that they're air tested so that there's no possibility of air getting in or water in the distance. They're then grouted up, cast in concrete, and the concrete itself is a special mix too. So we're here to have a balance. We want early age strength so that we can move the travelers out and not delay program. But at the same time, we need to make sure that these tendons have longevity for its 120-year design life. So it's a special low chloride mix to make sure that we reduce any chance of corrosion happening to the tendons. In the case of the top tendons, these get cast in concrete with a neck segment, so water should never be able to see the ends. Meanwhile, the bottom tendons are intended to just be left as is. So whilst they come to an end, we put a cap on them. That cap then gets spray applied waterproofing. We then also have a load of drainage holes in the bottom deck to ensure that if water ever does get in, it's not ponding. And hopefully that should ensure that these tendons, once installed, don't ever need to be dealt with again. Now, on paper, it all sounds well and good, but ultimately there are some changes that end up happening. We can plan as much as we want, but eventually something will come as a surprise. We've had some small changes and we've had some pretty significant ones. One of the major ones that I feel we should at least mention is the difficult ground conditions on the east side. Now, initially, it was designed such that we'd close off the east side, then cast the middle closing segment, then close off the west side. But because of the difficult ground conditions on the east pier fell behind, and as a result, the west side raced ahead. This meant that we were asked, can we change the sequence around? Now, whilst it sounds initially not too trivial to change it from east, middle, west to west, middle, east, the design, I don't know if you picked up in the drawings, isn't actually symmetrical. As a result, the loadings that would be locked in ends up changing. Thankfully, due to the model and the construction change in that, it meant that reworking this wasn't too difficult. And as a result, we were able to quickly work through, issue out some small changes to reinforcement, and then thankfully that saved the contractor approximately 3 months in time. Happy that you were able to listen to the whistle-stop tour of the design there before I hand over to David. We were thankfully able to look at what governs the piers, the free box arrangement, and how the complex geometry effectively makes this 3 different bridges. And then also how the post-tensioning works and how we've able to use that to lead to a very lean and efficient design. So thank you for listening to my bit. I'm going to hand over to David, and hopefully you can share some insights into the various different construction challenges we've had with this sort of construction.
Okay, thank you, Henry. First of all, my name is David Arribas. I work in FCC. FCC is one of the major Spanish contractor companies. I want to thank fibUK and Atkins to give us the opportunity to share our job in this project. And as well, I want to thank Tecozam. Tecozam is our main subcontractor in this bridge, and they have been collaborating in this presentation, and they are making a great job in this bridge. I want to share some previous experiences, FCC experiences with this construction methodology. These are some previous FCC experiences. We have been working in around 15 bridges with this construction system, balance cantilever with segments casted in place, and around 12 bridges balance cantilever, but with precast segmental bridges. This is a couple of examples. This is a bridge in Spain with 190 meters. This is another bridge in Zamora over the River Duero with a main span of 92. And the major bridge is this bridge with a main span of 180 meters in Mexico, San Marcos Viaduct. The most challenging part of this bridge was the height of the piers, with the main pier more than 200 meters of height. So our intention has been try to use some of this know-how that we have learned in this previous project in this bridge. Well, this is my sketch of the presentation. General ideas about the construction process, some comments about the forward travelers, some concepts about the segment lengths, closures, and stitches. This is the general view of the bridge, the lateral view. The main span is 75 meters. It maybe is a moderated span length for this kind of bridge, but well, the most challenging part was Henry has been explaining. The total width of the deck is very important, so it's necessary to split the bridge in 3 different boxes, and in a final stage we have to stitch connect all of these boxes. All the bridge is constructed in free balance cantilever up to this point, and in this point we are going to cast constructing this stretch of the deck over the scaffoldings. This is a plan view. We have split the bridge in 3 boxes: the on slip, the eastbound, and the westbound. We are progressing as 3 independent bridges, and in a final stage, we are going to widen in some parts of the bridge the wings of the wing of the top slab in a second stage, and we have to cast some stitches like this gray area and this yellow area. The general process in every deck is progressing with only 4 form travelers, 2 in every pier. The west pier is ahead of the east pier, so the progress is ahead in this pier. When we finalize the balance cantilever part in this pier, we have to close the deck against the scaffolding part. After this, we close the segment in the mid span, and the last step is close the lateral span, the east side. So the sequence is first the lateral span in the west, mid span, and the east span. This is a general view of the bridge progressing as a free balance cantilever. This is the west pier. This is ahead of the east pier. And as you can see, the balance situation is a key question in this kind of bridges. This is the situation right now, the construction right now, 2 or 3 weeks ago, with the on slip totally finished. We are working right now in the eastbound deck. Tecozan is progressing rather fine. In a few weeks, we are going to finalize the eastbound deck. And after this, we have to start the eastbound deck. Some words about the balance cantilever construction. Is very important, a good correlation, a good coordination between the contractor and designer, because every necessary unbalanced situation that is going to be on site is necessary to communicate to the designer and double check the situation. The designer has to evaluate any unbalanced situation due to the wind, but the contractor has to provide, if it is necessary, any additional equipment to place over the deck. But well, the advice is not place this kind of equipment. The usual approach is you have to place any heavy equipment, place this equipment over the pier, not in the tip of the cantilever. But for example, the casting of the segments is impossible to cast both segments at the same time. It's necessary to cast one segment, and after this, balance the situation. To not the temporary unbalanced situation, pier can resist. This is the standard cycle for a usual balance cantilever bridge casted in place. First of all, the installation of reinforcement. The second is the pulling of the segments, not necessarily simultaneously. After this, the post-tensioning of the top prestressing. Before launch any traveler, is necessary a geometry control to double check if we are progressing in the right geometry. After this check, we can launch both travelers and make the setting out of the travelers. If any correction is necessary, we can implement this correction in the next setting out in the next segment. The usual cycle that we are achieving is between 2 weeks and 1 week. 2 weeks in the first segments because the size is bigger. But in the last segments where the total height of the deck is less, we are achieving 1 week. The geometry control is a key question in this kind of bridges because it's impossible to achieve the theoretical elevation without any set of precumbers. This set of precumbers is formed by 3 concepts. One concept is the precumber that has to be defined by the designer because they have to analyze the construction process, taking into account all the edges of all the segments. As well, they have to modelize all the steps in the construction sequence and all the creep and sink rates. The other concept is the precumber of the traveler itself that has to be evaluated by the traveler's designer. And finally, maybe any potential correction has to be implemented in the precumber if we realize that we are progressing in the wrong with the wrong geometry. A couple of tips about geometry control in the balanced cantilever construction. It's very important make the geometry control very early in the morning to avoid any movement due to the thermal gradient due to the sun radiation. This maybe is not very important in UK because as usually it's raining or it's a very cloudy days every day. But in other areas, it's a very important question. The bridge can move several centimeters day by day due to the sun radiation. Another question is avoid any unbalanced situation of loads during the geometry control because any small load in the tip of the cantilever can change all the geometry of the bridge. Now we are going to explain about the formwork travelers. This is the formwork travelers in Taf Fechan. The owner and the designer of this foam traveler is Tecozam. The approach is, as usual, two trusses that are placed over the webs of the deck to avoid any transversal deformations of the concrete, and a couple of rails to roll on the traveler during launching. The traveler has 3 different sections, the front section, the rear section, and the anchorage section. In the anchorage section, there are several vertical anchorages to avoid overturning the traveler during the pouring. This is an schematic view of a typical traveler. This is not the Taf Fechan traveler, it's from another project. The Tecozam travelers, the weight is something around 90 tons, but this is a very usual figure. 80, 90 tons, this is the usual weight of a traveler. The formwork is formed by 3 parts. The lateral formwork, other part is the inner formwork, and finally the bottom formwork. All of these formwork are resting in the front section from these hangers that are connected to the front side of the traveler, and the rear part during the pouring is connected to the previously casted segment to allow the continuity of the concrete. Some comments about the segment length. In this bridge, the segment length is 6.4 meters and the segment 0 is 14 meters. This is not a very usual figure. The usual approach is 5 meters of segment length. In this case, we are progressing with this approach and it's working rather fine. But maybe for longer span length, it's a better approach, a shorter length, shorter segment, because at the end, the unbalanced situation is reduced with shorter segments. The works on the tip of the cantilever is reduced, and the post-tensioning can be distributed more easily by the designer if we use shorter segments. The length of the segment 0 is a key segment because it's a key question because the segment 0 is the first part of the deck that has to be constructed without traveler. So you have to bear in mind that it's necessary to install a lot of temporary works to cast these elements. So it's important reduce as much as possible the length of this segment, but at the same time, it's necessary think how are you going to install the first installation of the travelers. This is a usual approach that FCC have used in many other bridges with a segment zero length of 12 meters, an installation of both travelers at the same time. This is not the approach. In this case, according to Tecozan preference, we have progressed with only installation of one traveler. After this installation, you can cast one segment, launch this traveler, and in this situation, you release enough room to place the second traveler. With this approach, the installation is easier, but you have to spend maybe more time during the installation of the travelers. But, well, this is the approach in this bridge, and, well, it's working rather fine. These are several general pictures about the construction of segment zero. As you can see here, there are a lot of temporary works to install the scaffolding, even are necessary some recesses in the pier. It's a very complicated element to be constructed because it's plenty of reinforcement, because all the unbalanced situation of the deck has to be transmitted through this part of the deck to the pier, because it's an integrated deck and pier connection. The closures, we can explain two different things: the closure in the main span and the closure in the lateral span. The closure in the main span, you have to avoid any relative movement between both cantilevers. These movements can appear due to the wind loads, any unbalanced load, thermal movements, or whatever. So it's necessary connect both parts of the cantilever with any temporary structure. In the main span, as these two strings of cantilevers, the stiffness is very similar. We have progressed as usual with the railways of the traveler. We connect both strings of the cantilevers with PT bars, and with this connection, we avoid any horizontal relative movements and vertical movements. We use for the closure of the main span the formwork of the traveler, and we cast in two stages. One stage with the web plus the bottom slab, and in the second stage, the top slab. After pouring and hardening the concrete, we can install the post-tension and the continuity post-tensioning, and we can then release this temporary connection. In the lateral span, the approach has been different because this part of the cantilever, the stiffness is very different from the part that is over the scaffolding. So additionally, this closure, we have used the formwork of the scaffolding instead of the traveler. So in this case, we have used the rails of the traveler to avoid the longitudinal relative movements, but the vertical movements, the downward movements of the cantilever is avoided thanks to the scaffolding, but the upward movement is restrained thanks to this ballasting load that we have applied in this area. The pouring of this segment is split as well in two stages. One stage with webs plus a bottom slab, and the second stage only the top slab. After hardening of the concrete, we can place the post-tensioning and make the continuity. This is a general view of the closures in the lateral span. Here we are casting the top slab. This is the rails connecting the tip of the cantilever and the tip of the cantilever and the part of over the scaffolding longitudinally, and the ballasting load, avoiding any uplift movement of the tip of the cantilever. And this is the general view after finalizing the closure segment in this area. Finally, some ideas how we are going to address the stitches. Tecozan has designed and is fabricating a set of travelers that we are going to use in this final step. The approach is use a traveler that straddle the loads between these two adjacent boxes, and we are going to pour something around 10 meters long. Well, the elements are right now under fabrication, and I think in a few months we can have these elements on site and to finalize the bridge. And that's all. Thank you very much for the attention.